Imagine a ghost, something that can pass through walls, through you, through the entire Earth without leaving a trace. Now imagine trillions of them are passing through your body every single second. These aren't spirits from a spooky story, they are real particles, born in the heart of stars, in violent cosmic explosions. And even in the first moments of the universe itself, we call them neutrinos, the ghost particles of the cosmos. For most of human history, we didn't even know they existed. They were completely invisible to us, carrying secrets from the most extreme and distant places in the universe, their messages flying right by, unheard and unseen. Hunting them is one of the greatest challenges in science. How do you catch something that barely interacts with anything? You can't build a net strong enough, you can't put up a wall thick enough. These particles are so elusive, one could travel through a block of lead a light year long, and still have only a 50-50 chance of being stopped. So scientists had to think differently. They had to build a trap not of strength, but of patience and probability. They had to create a space so vast, so pristine and so carefully watched, that on the off chance one of these billions of ghosts interacted, they'd be there to see it. Deep beneath the rugged peaks of Mount Aikano in Japan lies a cavern of staggering proportions. It's not a natural cave. It was carved out by human hands a kilometer underground, shielded by solid rock from the rest of the world. Inside this cavern sits a colossal, gleaming golden cylinder, 40 meters tall, 40 meters wide. It's large enough to comfortably hold the Statue of Liberty. This is Super-Kamiokande, or Super-K for short. It is not a telescope that looks up at the sky, but a detector that peers down through the Earth, waiting for particles to arrive from the other side of the planet. It is a cathedral dedicated to science, a silent, waiting sentinel. Why build such a magnificent structure so deep underground? The surface of our planet is constantly showered with cosmic rays, high-energy particles from space. This cosmic static would overwhelm the incredibly faint signals that scientists are looking for. The kilometer of solid rock above Super-K acts as a natural filter, a massive shield that blocks out almost all of this background noise. Only the elusive neutrinos, which barely interact with matter, can pass through the entire planet to reach the detector from below. By placing it deep within the Earth, scientists created one of the quietest places on the planet, a perfect listening post for the whispers of the cosmos. The sheer scale of the detector is mind-boggling. The tank is filled with 50,000 tons of water so pure it can dissolve metal. It's some of the purest water on Earth, constantly filtered and monitored to remove any impurities that might obscure a signal. Lining the inner walls of this massive tank are more than 13,000 golden orbs, each one an incredibly sensitive light detector called a photomultiplier tube. These tubes are the eyes of Super-Kamiokande. They sit in the darkness, waiting patiently for the faintest flash of light, the telltale sign that a ghost particle has finally revealed itself. So what exactly is this ghost particle we're hunting? A neutrino is a fundamental particle like an electron or a quark, but it's very, very different. It has no electric charge, which is why it doesn't interact with the electromagnetic forces that hold most matter together. It also has an incredibly tiny mass, so small that for decades, scientists thought it had no mass at all. These properties are what make it so ghostly. It doesn't feel the push and pull of electromagnetism, and its tiny mass means gravity barely affects it. It is the ultimate cosmic introvert, traveling through the universe almost completely undisturbed. Neutrinos are everywhere. They are one of the most abundant particles in the entire cosmos, second only to photons, the particles of light. Our own sun is a tremendous neutrino factory. The nuclear fusion reactions happening in its core, the very reactions that produce the light and heat that make life on Earth possible, also produce a staggering number of neutrinos. Every second, more than 100 trillion neutrinos from the sun pass through your body. These particles are cosmic messengers. Because they travel in straight lines and barely interact with anything, they carry pristine information directly from their source. They give us a direct window into processes that are otherwise completely hidden from view. By studying them, it's like we're able to put a stethoscope right on the heart of a star and listen to its inner workings. With 50,000 tons of ultra-pure water and 13,000 electronic eyes, Super-Kamiokande waits. It doesn't catch the neutrino itself. Instead, it waits for the neutrino to do something incredibly rare, interact with the water. Once in a very, very great while, a neutrino will strike the nucleus of an atom in a water molecule. A direct hit. The odds are astronomically low, but with trillions upon trillions of neutrinos streaming through the massive tank every second, astronomically low actually happens about 30 times a day. When this collision occurs, it can produce other charged particles like an electron or a muon. Now here's the beautiful part. These newly created particles fly off through the water. And if a particle with an electric charge moves through water faster than light moves through water, it creates a shock wave of light. This isn't a violation of Einstein's theory of relativity. Nothing can travel faster than the speed of light in a vacuum. But light slows down when it passes through a medium like water, so it's totally possible for a particle to outpace the light in that specific medium. This shockwave of light is called Cherenkov radiation, and it's the key to seeing the invisible. This Cherenkov light erupts as a cone, a pale blue flash that spreads out through the dark, pure water. It's this cone of light that the 13,000 photomultiplier tubes are waiting to see. When the light hits the tubes, they convert the light into an electrical signal. Computers then record which tubes saw the light, how bright the light was, and precisely when it arrived. By analyzing this information, scientists can reconstruct the event. They can figure out the direction the neutrino came from, how much energy it had, and even what type or flavor of neutrino it was. The pattern of the light tells the story. Think of it like this. The neutrino is a silent, invisible bowler. The water molecules are the pins. Most of the time the ball passes straight through without hitting anything. But when it finally hits a pin, you don't see the ball itself. Instead, you see the pin go flying. By watching how the pin moves and where it goes, you can figure out everything you need to know about the ball that hit it. The Cherenkov light ring is the signature of that impact. A sharp, clear ring means one type of neutrino interaction, while a fuzzy, scattered ring means another. In the silent darkness of Super-K, these faint blue rings are like smoke signals from the subatomic world. For decades, physicists were puzzled by something called the solar neutrino problem. Our models of the sun predicted a certain number of neutrinos should be streaming towards Earth. Yet, experiments found only about a third of that number. Where were the missing neutrinos? Was our understanding of the sun wrong? Or was something strange happening to the neutrinos on their 150 million kilometer journey from the sun to the Earth? Super-Kamiokande was built to solve this mystery. The detector confirmed the neutrinos were not missing. Instead, they were changing. Diagram: neutrino flavor changing as it travels sun to Earth. Neutrinos come in 3 different types or flavors: electron, muon, tau. Early experiments were mostly sensitive to just one type, the electron neutrinos produced by the sun. Super-K's data provided definitive proof neutrinos change identity mid-flight. An electron neutrino leaving the sun could arrive at Earth as a muon or tau neutrino, which earlier detectors would have missed. This phenomenon, called neutrino oscillation, was groundbreaking. Throwing a baseball turning into a football, then a basketball, the discovery implied neutrinos must have mass. According to quantum mechanics, for a particle to change identity over time, it must have mass. This discovery shattered a long-held assumption in the Standard Model, which had predicted neutrinos were massless. It was the first major crack in our most successful theory, pointing the way towards a new understanding of physics. Super-K didn't just find the missing solar neutrinos, it opened a new realm of physics. Beyond the sun, Super-Kamiokande stands as a galactic sentinel, waiting for the most violent events in the universe. When a massive star runs out of fuel, its core collapses, and it explodes in a supernova. This explosion releases an almost unimaginable amount of energy, and 99% of that energy is carried away not by light, but by neutrinos. In 1987, before Super-K was built, its predecessor detected a handful of neutrinos from a supernova in a nearby galaxy. If a supernova were to happen in our own Milky Way today, Super-Kamiokande would detect thousands of neutrino events. This flood of data would give us an unprecedented second-by-second view into the heart of a dying star, a spectacle otherwise hidden from our eyes. The discovery of neutrino mass was not just a minor correction to our textbooks, it was a seismic event in the world of physics. The Standard Model of particle physics is one of the most successful scientific theories ever conceived, accurately describing the behavior of all known fundamental particles and forces with stunning precision. For decades it stood as a nearly complete description of the subatomic world, and in that model, neutrinos were massless. Super-Kamiokande's proof that neutrinos oscillate and therefore have mass was the first piece of experimental evidence that the Standard Model was incomplete. It opened a door, a crack in the edifice of our knowledge, revealing that there is more physics out there waiting to be discovered. This single discovery has sent physicists back to the drawing board, inspiring a wave of new theories and experiments. Understanding neutrinos is crucial for understanding the universe. Their properties are woven into the fabric of the cosmos. Their tiny mass, while almost nothing, adds up. With so many of them in the universe, their collective gravity can influence how galaxies form, how the universe evolves on the largest scales. Furthermore, the strange behavior of neutrinos might hold the key to one of the biggest mysteries of all: why the universe is made of matter. In the beginning, there should have been equal amounts of matter and antimatter, which would have annihilated each other, leaving nothing but light. Something tipped the scales, and neutrinos might be the reason why. Why does this matter? Why go to such extraordinary lengths, carving out a mountain, filling it with ultra-pure water and waiting in the dark for ghostly particles, to understand something so small and so elusive? It matters because this quest is fundamentally human. It is driven by the same curiosity that led our ancestors to look up at the stars and wonder what they are. It is the desire to understand our place in the cosmos, to read the story of the universe and to find our connection to it. The discoveries made at Super-Kamiokande are not just for physicists. They belong to all of us. Every time we learn something new about the universe, we learn something new about ourselves. The knowledge that neutrinos from the sun are passing through us connects us directly to the star that gives us life. Realizing that these particles change their identity on their journey reminds us that the universe is a dynamic, surprising place, not a static machine. Learning that the properties of these tiny, ghostly particles might be the reason we exist at all, the reason there is a universe of matter to form stars, planets, and people, is a humbling and awe-inspiring thought. We are made of stardust, and we are moved by ghost particles. Science is a journey, not a destination. Each discovery, like that of neutrino mass, does not close a book, but opens a new chapter with even more tantalizing questions. The work at Super-Kamiokande is a powerful reminder that there is always more to explore.